Hi and welcome to Lab 4 Circuits. Some introduction is that the purpose of this lab is to predict the behavior of circuits, use multimeters to measure conventional current and potential differences, and examine the behavior of resistors and capacitors. Some concepts we're using today include the loop and node rule, charge conservation, steady state, Ohm's law, resistance, and capacitance. Some assumptions we made were that the resistance in wires and ammeters is negligible, and that the EMF is equal to the potential difference of capacitors and plus the potential differences of resistors. The main results of this lab include that experimental values match theoretical values and that the current in an RC circuit is time dependent. So for the first part of this experiment, we had a circuit with two 1.5 volt batteries, two ammeters, and two resistors, 47 ohms and 100 ohms. So we predicted the current to be 0.02 amps, using the Ohm's law. EMF is equal to current times resistance. We solved for current and got that, and then in the ideal simulation we also got the same thing, so they did match. When the ammeter is read or is inserted backwards, it's read as a negative. Now we replace the ammeter with a voltmeter, and the current goes to 0, and this is because it's now an open circuit, so there's nothing flowing in between this gap. And then the potential difference is 3 volts, which is just from the battery's sum. Then we use the voltmeter to measure the potential differences between these points listed here, and we got these values. The net delta V is equal to 0, which checks out. The current is back to 0.02 when we make it close, and this is because the voltmeter does not affect it at all due to its high resistance. Here is a graphical representation of the points we just showed and how it decreases. Then we created another circuit or series in parallel with a 100 ohm resistor, and this increases the current to 0.06. And this is because the current is now being split at this node, so now all of it is experiencing the resistance from this resistor, and that increases it. And the new resistances are calculated by current divided by potential difference. We got 48 for this one and 102 for this one. So for the second part of the experiment, we explored an RC circuit. So we had two bulbs, 10 ohms and 20 ohms, one 9-volt battery, and a 200 millifarads capacitor. So with the battery, the 10-ohm bulb, and the capacitor, we had the light brighten quickly and die out. The capacitor is being charged and the current decreases to 0. When you take the battery out and you create this circuit, the light also brightens quickly and dies out, but the capacitor is discharging and the current decreases to 0. I timed this for both bulbs and got these results. Now we recreated this with a 30 ohm light bulb, and we timed the discharge of the capacitor as well as the potential difference. We linearized the data and got this line of best fit for the graph. We calculated the RC, or the time constant, using the slope and got 5.97 seconds, and then we calculated the theoretical RC, which is resistance time capacitance, which is 6 seconds, so they're very similar values. Some questions you can ask are, what if we were doing this lab in real life and use an actual ammeter? So an actual ammeter would have had some resistance instead of 0 resistance, and this would have caused the current to decrease since it would be experiencing more resistance. And what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor? So with no resistance, our capacitor would have reached full charge immediately. However, this would never happen in real life since wires connecting the batteries and capacitors would always contain slight resistance. So some conclusions. Our possible sources of error in this lab include using the stopwatch for human error, but mainly there were no errors since we used the ideal simulation. The main results of this lab are that wires and ammeters must have 0 resistance to calculate accurate values. Currents and voltages are time dependent. Ohm's law, the node rule, and the loop rule are important tools used to analyze circuits. Thanks for watching.